All right, so we're in section 11.4. We're going to talk about the cross product. All right. So the cross product. Cross product is another kind of vector multiplication. So we'll define the cross product, and then we will talk about how we find it, and then we'll talk about the properties. That's really the point of today's lesson, is just kind of an introduction to the cross product. Cross product is only defined for, you need to be in 3 dimensions to talk about the cross product because of one of the special properties of the cross product. So we're going to say U is our vector u1i plus u2j plus u3k, so our components there, and we're going to say that v, our components for v, when I wrote my v's, someone sent me on Facebook last night, it was a picture of the Vans logo that looks like this, sort of. And the question was, there's a picture of a t-shirt, why does your t-shirt say square root of the answer? And now I can never think of Vans as anything else than the square root of the answer. You guys are a little, did you forget your Starbucks this morning? All right, so these are our vectors. Our cross product, U cross V, is this kind of complicated looking thing. So here's our cross product written out. So that's if we write our vector in component form, this is what the cross product looks like. It's only defined for 3-dimensional vectors. And one important property is that U cross V is orthogonal to both U and V. So that's one property of the cross product that we're going to take advantage of a lot. And now we're prepared to answer another important mathematical question. Why did the vector cross the road? To be normal. Okay. So I know that we've seen the cross product before. The way that an easier way to calculate it than remembering all of this is with the determinant form. So if we write out U cross V, and this is how you'll normally do it. We're looking at this determinant I, J, K, U1, U2, U3. So we think of it as a determinant. And then there are several ways that you can evaluate this determinant. The way that I usually do it is for the I component. You write out your I, and then you cross out. I'm going to do some dotted lines here. So you would take your I component, and then you would cross out those two, and you would multiply U2 times V3 minus U3 times V2. So you take the determinant of the smaller one. Have you all done that little procedure before? To define the determinant. And then for the J component, you do the same thing for the J. You cross that out, and then you take the determinant of the 2 by 2 matrix that's left inside there. The important thing to remember about the J component is the J component is negative. It has this negative sign. So when you find your J component, make sure that's the most common mistake with cross products that students make is they forget this negative sign. So the J component's negative, and then for the K component, you would do the same thing. You would cross out those two rows, and you would find the determinant of the 2 by 2 matrix that's left. Positive when you're going diagonal this way, negative when you're going diagonal that way. And that's exactly what we have up here. Another way to think about it, if it helps, is you can write the first 2 rows outside here, or the first 2 columns. And then for this, we would do our I component would be I times this minus I times this as I go on the diagonal. My J component would be J times these two minus J times those two. And then my K component would be K times these two minus K times these two. So you can also write out your cross product that way. Anybody unclear on how to find the cross product using this determinant method? So usually the people you've done that before, the students are familiar with finding that cross product. All right. So let's do a quick example of finding a cross product, and then we'll talk about the properties of the cross product. Some of the properties of the cross product are this orthogonal property is one very, very important property, and a couple of the others that we'll use quite a bit in second semester. All right, so we want to find, we're just going to calculate a cross product. So we're going to find A cross B, where A is 2I plus J plus K, and B is negative 4I plus 3J plus K. So I'm going to write out this is how I go about finding my cross product. I write out the determinant. If I don't write it out, I know some people can kind of do this in their heads. If I don't write it out, I always make mistakes in my sign. I get a minus sign wrong somewhere. So I always write it out like this, and then I'm just going to go component by component. So this is going to be I hat times 1 minus 3. Minus J hat times 2 minus negative 4. So 2 plus 4. And plus K hat times 6 minus negative 4. So I always have to write it out like this, or I make mistakes in my arithmetic. So this is going to be minus 2I hat minus 6 J hat plus 10 K hat. So that would be my cross product. Questions? Did we, I'm just double checking, did we calculate this correctly? Yeah. So I was, and we said that the cross product was orthogonal to both A and B. So I was double checking that our dot product that's orthogonal, then our dot product is going to be 0. So the dot product of A and B is 0, or the cross product with A is 0, and the dot product with B is 0. So I was double checking to make sure I didn't make a mistake in my arithmetic. So the most common mistake with a cross product is ending up with one of these signs, the positive or negative, incorrect, and then your cross product ends up wrong somewhere. So questions on calculating cross products? All right, let's talk about some of the properties of cross products. So first we want to talk about the algebraic properties. So in addition to the cross product being orthogonal to our vectors, oops, that's not what I wanted to do. There we go. I want to turn that into a solid line. There we go. In addition to the orthogonal property, there are some algebraic properties that are interesting. The first one is that the cross product is not commutative. So if we change the order, we change the sign. So U cross V is negative V cross U. We can distribute with the cross product. As long as we pay attention to the order that we do the operation. So this could be, we can do this as U cross V plus U cross W. We can multiply by a scalar. So if we have a scalar times a cross product, this is going to be CV cross W and that would also be V cross C times W. And here C is a scalar. So I can multiply the scalar by either one of the vectors to get my cross product there. If we form a cross product with the 0 vector, we get the 0 vector. This is not a scalar. The cross product of a vector with itself is the 0 vector. And then we have a triple product, U dot V cross W. We won't do a lot with this, but this one's an interesting one. This is also equal to u cross v dot w. And this is called the scalar triple product. Or the box product. And I'll talk about the box product again in just a little bit. So those are our algebraic properties. The most important one to remember is if we change the order of our cross product, we change the sign. So we have to pay attention to the order that we do the cross product. We have to, and that changes the direction of our orthogonal vector. So now we're ready to answer another important mathematical question. What happens when you cross two mountain climbers? You can't. They're both scalars. Okay. So this is how we do some of the algebra with our cross product. Now we want to talk a little bit about the geometric properties. So for our geometric properties, we're going to say theta is the angle between our two vectors. So just like we did with the dot product, often we're interested in dealing with the angle between the two vectors. That's our angle between our u and v. We stated our first one already, that u cross v is orthogonal to u and v. So that's an important one. The magnitude of the cross product is the magnitude of u times the magnitude of v times sine theta. Oh, and I wrote single bars instead of double bars. I'm talking about the magnitude of the vector here. So I said sometimes I forgot and wrote. I always, when I learned vectors, we only use single bars. So sometimes I forget to write the double bars for the magnitude. So the magnitude of u cross v is the magnitude of u times the magnitude of v times the sine of the angle between them. And our third one is that the cross product of two vectors equals the zero vector if and only if these two vectors are parallel. So if and only if u is parallel to v. And the other way we could say that is if u is a scalar multiple of v. That's how we can, another way that we can say parallel. We'll take advantage of this next one a lot second semester. The magnitude of u cross v is the area of the parallelogram with u and v as adjacent sides. So if we had something like this, the magnitude of the cross product, this is u and this is v. If I complete this parallelogram, U cross V is the area of that little parallelogram. And we're going to use that to calculate things when we start talking about surfaces. So we'll talk about the area of a surface. We'll use the cross product comes up with the area of a surface in 3 dimensions. And then our box product or our scalar triple product, our geometric property, U dot V cross W is the volume of the parallelepiped, so a little prism shape, but it can be slanted. With these 3 vectors as adjacent sides. Oops. U comma V comma W as adjacent sides. So what we're talking about there is if we have 3 vectors like so, and this one, I'll make this one slanted. So we have these vectors in 3 dimensions. If we completed this little shape, like so, and we could say this is U, V, and W down here. These 3 vectors U, V, and W are adjacent sides. This scalar triple product would give us the volume of this little solid. So that's another interesting geometric property involving the cross product. We don't use this one as much, but we do definitely use this one. Now we're ready to answer a third important mathematical question. What do you get when you cross an elephant with a zebra? Elephant, zebra, sine theta. Elephant, zebra, sine theta.
Oh, okay.
Okay.
That's funny.
Well, yeah, we could get you guys a little more fired up for your next class. All right, I just want to look at one other example, one other type of problem that you'll have to do in your homework. Just a different way of interpreting the cross product, and that's all I have for today. So this type of problem shows up frequently, not just in this homework, in our second semester when we're talking about surfaces in space. This kind of question comes up a lot. So we need to find a vector orthogonal to both A equals I plus 2J minus K, and B equals minus 2I plus 2J plus 2K. So we want this vector that's orthogonal to both of these. So what is this question asking us to do? Find the cross product. You'll be asked, or this kind of problem will be presented to you in a lot of different ways. So it's important to remember that the cross product of 2 vectors is orthogonal to both of them. We're going to use the cross product to find when we start talking about planes, we'll start talking about the equations of planes. We're going to use the cross product. For planes, we define a normal vector to the plane. So we'll use a cross product to find the normal vector. When we start talking about surfaces, we want a vector that's normal to the surface. So we have to, we'll have to find, we may use cross products to find a normal vector to the surface, to a three-dimensional surface. We'll talk about normal lines. So we'll talk about the intersections of surfaces, and we want a vector that is normal to the curve of intersection. So we end up finding a cross product there to find our normal vector. So this type of problem comes up in a lot of different ways in a lot of different disguises. So basically we're just going to calculate our cross product. So A cross B is orthogonal to both. So form our cross product. Let's take a look at this process again. So I'm writing out this in determinant form, and I'm going to write each piece. So this is I times 4 plus 2 minus j, remember this minus sign, times 2 minus 2 plus k times 2 plus 4. So we get 6i, and we get 0j, and we get 6k. What if the problem asks us to find a unit normal, a vector that's orthogonal to both a and b, a unit vector orthogonal to both a and b? What would we do for that? Divide this vector by its magnitude. That would give us a unit vector. What would we get if we found b cross a rather than a cross b? It would just point the opposite direction. It would still be orthogonal to both. It would just point the opposite direction. Let's see, one thing I didn't talk about in the geometric properties is the right-hand rule. The direction of our cross product is, I think of the cross product as an action. So if our finger points in the direction of one vector and the other vector is pointing out from our palm, the direction of the cross product is the direction that your thumb is pointing. So I think of crossing one vector onto another. I think of it as an action. So I'm crossing my fingers onto my palm, and my thumb points in the direction of the cross product. Some people think of it this way, with their fingers kind of situated like this, and your thumb points in the direction of the cross product. It helps me to think of it as an action. I'm crossing one onto the other, and that helps me get the direction. Am I crossing it this way? Am I crossing it that way? Which way am I crossing? All right, so we use our right-hand rule to find our direction of our cross product. Any questions on the cross product? Okay. On Monday, we'll talk about some applications of the dot and cross product. All right, there you go.